Okay, quick little thing about chirality and carbohydrates and why we care. So first off, most of the carbohydrates we see are going to have more than one chiral center. So carbohydrates most of them are chiral. There are a few that are not, but most of them are chiral. Most of them have chiral centers. Most of them have many more than one chiral center. Here's a very simple small one that has two chiral centers, because this carbon has the aldehyde up here and has hydroxyl and then the hydrogen. This has a hydroxyl, a hydrogen, this group, and then this whole group up here is also different. So these are different groups. So the reason we care about handedness is because something that is chiral reacts differently. Actually, I should say something that is chiral means that you have two enantiomers, right? You have two enantiomers. The two enantiomers are going to react the same if they're reacting with a substance that's achiral, like water. If you dissolve two different enantiomers in water, their solubility in water is going to be the same, because water is achiral. Water does not have four different groups bonded to it. But if you dissolve them in, say, 2-butanol, right, you're going to get something a little bit different. You're going to get, you have four different groups. This carbon is a chiral center. Two different enantiomers are going to dissolve, have different solubilities into butanol. So in other words, the analogy your book uses, and the analogy I like, is if you think about a baseball player. A left-handed baseball player needs a baseball glove that fits on their right hand. Well, they can't use the other-handedness of glove. Gloves are chiral, right? So your hands are chiral, and you have to interact with a glove. The glove is also chiral. So that which hand is interacting with the glove matters, because the glove is chiral, your hand is chiral, so there's a difference in how well it fits. So your left hand can't fit in a right glove. A bat is completely different. A bat and its mirror image, aside from superficial markings, if you look at the shape of it, a bat and its mirror image are the same thing. They are not chiral. They don't have handedness. There's no such thing as a left and right-handed bat, right? It's just a stick. So both a left and right-handed person can use that exactly the same. It's sort of like a hammer also. If you think about left-handed people have trouble using scissors because scissors are chiral, right? Because the way the two things lay together. A hammer is not. So a left-handed and right-handed person can both use the same hammer. That's not a problem because it's not chiral. It's achiral. But the scissors are chiral, so you have left-handed and right-handed scissors, and it's hard to use with the incorrect hand. The same is true in chemistry. Two different handednesses of a molecule, an enantiomer, two enantiomers of each other, will interact differently with other chiral things. Predominantly, this is important because in the human body, most of the compounds in the human body are chiral. So this is really important for the pharmaceutical industry, where a left-handed drug and a right-handed drug have vastly different reactivities. A right-handed drug might have beneficial effects, and its opposite, its enantiomer, may be toxic or do nothing or have a diminished effect. It can be all over the map. But so chiral things, two enantiomers will interact exactly the same if they're interacting with something that's achiral, but they will act differently with chiral things.